I am Graham Anderson. I'm an advanced chemist at the Wisconsin State Laboratory of Hygiene. Today I'm going to basically run out total phosphorus on a latch at 8,000 and just tell you about what I'm doing and basically how it works, I guess. Basically what we're doing in the lab here, this is inorganic wet chemistry, State Lab of Hygiene. Our biggest customers are Department of Natural Resources and United States Geological Survey, where they're doing a lot of surface water monitoring and/or some projects. Doing the analysis, we are doing our solids analysis, BOD, pH, chlorophyll, color, turbidity, kind of on the other end of the lab that are more basic physical type stuff. This end of the lab, we're doing primarily nutrients, ammonia, nitrate, fluoride, sulfate, chloride, total phosphorus, orthophosphorus, silica, TKN, those kind of things. We also do drinking water analysis for nitrate and fluoride for private customers, and also municipal wells around the state have to send in a monthly split for their fluoride testing to make sure that their testing agrees with our testing, just kind of as a double check. So we do that also. This is a latch at 8,000. It's run by a PC. We have three major components: an auto sampler, which is has a probe and goes in XYZ coordinates and it'll sample. A peristaltic pump that'll bring the sample and reagents to a manifold that will mix the reagents, past a colorimeter at 880 nanometers that will measure the amount of absorbance, which will be proportional to how much phosphorus is in in the sample. Another way of thinking of this is, I think of it as an automated spectrophotometer. If you've ran simple colorimetric chemistries by putting some reagents in a sample in a test tube, you shake it up, it turns color, you put it in a spectrophotometer, it reads the absorbance. That's basically what's going on here, but in a much different automated way, that when everything's working right, I can walk away for a large amount of time and do something else in the lab, which makes it a very useful instrument. Basically, this is a sampler, which is going to bring samples, whether it's standards, which I have back here, or unknowns, to our instrument to analyze. And what's going on at the instrument is, instead of having a test tube that we're putting known amounts in, we have different size pump tubes that are proportioned to bring in the right amount. These two mix together as a color reagent. This is just a carrier. So we have a color reagent here and here that come together, and a carrier, and those are all coming into this manifold. Instead of mixing stuff up in a test tube, we have things proportioned into T's and a little mixing coil, and everything mixes together so we have the right mix. So the color reagent and carrier and everything is all ready for the sample. The sample comes into this valve, loads this sample loop, the valve toggles and injects this amount of sample. That reaction happens here, and a blue color develops. It's proportional to the amount of phosphorus. Goes through a flow cell. There's a light source shining a light, very similar to a spectrophotometer. We have a filter here at 880 nanometers and a detector on the other side. So that's how our absorbance is read. That absorbance is proportional to the blue color. So the higher the absorbance, the more blue color, which from a standard curve we can figure out our concentration of phosphorus in an unknown. The sample has come past the detector and has had this blue color develop. We come out, basically it's a waistline. The waistline traces back kind of underneath the instrument and just comes to a jug. In our carboy here, we collect this waste because it is acidic. It's not anything hazardous as far as the chemical content. It's just we have to neutralize it to between, I think it's 5 and 7, 5 and 9 or whatever. We neutralize it and then we can actually just pour it down the drain, but we do have to neutralize it. Like I said, a colorimetric chemistry in a test tube at a spectrophotometer. This is just an automated system for doing the same thing, where I'm able to do approximately 150 samples today, where I think the most I've done by hand at a spectrophotometer is maybe 40 to 50. Prior to today, these samples were set up and digested. That we get, these are mostly surface water samples from Wisconsin Department of Natural Resources, United States Geological Survey, basically doing monitoring of various surface waters and or some compliance limits for possibly a wastewater treatment plant or a fish hatchery or something are some of the more interesting samples that may be in there. So I'm going to have to transfer these to a smaller test tube that'll fit on the sampler. A couple of these reagents we degas with helium. If you can imagine, if you shake a can of pop to get rid of the fizz, basically bubbling the helium through, we're driving off any dissolved gases, and what that does is prevents bubbles from forming during the analysis, because bubbles cause problems in the instrument. I'm going to get the reagents going here just so the instrument's ready to go. This is a peristaltic pump and has rollers that through peristalsis will move the reagents into the instrument, and what will be going in here is water, a color reagent, and then a carrier is what's going into this manifold. And the pump tubes are different diameters to proportion things correctly. So right here is an acidified carrier that matches how much the samples are acidified. This is going to an ascorbic acid reagent, which is part of the color reagent. And this one goes to the ammonium molybdate, which is the other half of the color reagent. It turns a blue color that's proportional to the amount of phosphorus. Sometimes you can see, if it's going to turn blue, you'll see the blue color before it goes past the flow cell, and the detector detects it. That's just to keep anything from falling in there. Two things I didn't show you here is, once the color does develop, it goes through a flow cell and light shines through from the bottom, and a detector will detect the absorbance, and this is a filter at 880 nanometers. That is the wavelength where the blue color is most sensitive for the absorbance. So now we have our reagents going. One thing I do have to do is I have to find the run in the instrument in the software itself. So basically this tells the instrument what samples it's going to be running and where they are in the racks. What information is in here is there's a standard curve that I'm giving it knowns, so it can establish a curve, and then from that curve it can analyze unknowns. I have some quality control samples to begin with. Then these are non-point samples for phosphorus, our unique lab number that links it to the person, what their site is, and so we can send them the results. But that's the unique number that we can send back into our lab information system. And in this run we have 186 tubes that we'll be analyzing for phosphorus in one way or another, whether it's an unknown sample, quality control sample, or other things. And once we get going, I can show you what's going on these. We have three basic windows. What's on the sampler, what's going on past the detector here, and then this is actually the results kind of spitting out in this report window. Basically, I have to pour these into smaller tubes so they'll all fit on the sampler. We have to use a larger tube to do the digestion because it just needs more room for the digestion, for expansion, and if it bubbles at all or anything. But I'll be pouring it into a much smaller test tube to fit on the instrument so I can fit those 186 test tubes in a small place. Right now I'm pouring the standards, which are known concentrations of phosphorus. And from those known concentrations we'll create a calibration curve. Then the instrument will know how much phosphorus is in each sample from that curve. And we pretty much all set these up the same way, so But by either putting labels on things or knowing what spot they're in, or usually it's just a consecutive numbering thing where I know this is number 1 and I know this is 40,
Yeah.
and they line up with a cup number on the instrument. These larger ones at the end, it'll run one every 10 unknowns. That it's a check standard and a check blank just to show the instrument is still in calibration and has not drifted. And this is what we call our standards rack, because these are only standards, and it'll go back there to establish our curve. These spots, 1 through roughly 280 or something spots, are where we'll put the samples. So each one of these test tubes has a slot which lines up with the numbers that I showed you there before on the piece of paper. This is the not so exciting part. I have to pour 186 larger tubes into smaller tubes, but that's the only way it all fits. This is our normal sample container for total phosphorus. We get 250 mils that's acidified with sulfuric acid, and we can take ammonia, nitrate, TKN, total phosphorus, those nutrients out of this bottle. So that is what we start with. I only need about 25 mils for a total P analysis. Each digestion is 8 mils, but if I were to have a duplicate and a spike, then I would need about that 25 to 30 mils. So this bottle will go usually a long way unless we drop it. To a certain extent, I have to rush because it takes approximately 2 minutes to run each one of these samples. If I don't get started, I won't get out of here today. We get approximately, when it's busy in summer, 300 or more of these a week, and run out about 300 or so a week if everything's going well. So it's definitely one of the tests we run the most of. I'll have to pour more of these as I go, but just to get the instrument going, because time is a factor, that we have an 8-hour day and there's about 6-7 hours worth of samples to run. So I have my samples loaded, I have my standards loaded, and I will start the instrument, and the probe will go to whether it's a standard or a sample, and it knows this from the software and what we've entered. Basically, it's almost as easy as pushing start. So here we have a sampler going over to a known standard, which concentration is 1 part per million phosphorus. And it'll go through these and establish its standard curve, and then we'll keep going and do unknowns as long as all of our quality control things work at the starting of the run. The quality control that I have at the beginning of this run are a blank, a lab fortified blank, and a quality control standard that's another source of phosphorus, just to double check that my concentrations are correct. So this peak represents how much blue color basically is going past that detector. And what the instrument will do here is it'll figure out the peak area, which it just did, and it'll plot these peak areas in a standard curve to establish that calibration curve. And this is one of 6 standards that it will take to establish that curve, and once we get those 6 standards through the instrument, we can take a look at that curve. And our basic criteria for that curve is it has to have an R of 995 or better, that it is linear. And we can look at that in a few minutes once that is done. Otherwise, it's we just have to sit here and wait for a bit until the calibration curve goes through, establish that's passes everything, and then we can start looking at unknown samples. So right now, we're running our 6 standards to establish our curve. Right now, there's only 2 points plotted. Here we can see our known concentration of 1. The instrument plots peak area as volts per second. So it says the first one's 32, the next one's 16 something, and a little bit here, 0.025 should be coming out, which is actually, that's coming through right now. So in half a minute or so, it should plot that point, and we should see it appear. And basically, as long as we have an R of 99, a correlation coefficient of 995 or better, we should be able to run there. That third point popped out. We still have a real good correlation, very near 1, all 9s and a 5s. These 6 points that we're running for this curve, which we can see they're here in this standard track, are 1 part per million, 0.5, 0.25, 0.05, 0.016, and 0 are known concentrations of phosphorus that we've put into this digestion and digested. And then right now we're running these to establish a calibration curve. And from this curve, whatever the peak area is for an unknown sample, we can take that peak area and know how much phosphorus it is in it. And the software does this by plotting the points and figuring out the peak area. Years ago, you could do this by measuring the peaks with a ruler, and actually remember doing that for some classes. But with the new software and the instruments, it's a lot easier than it used to be, and it works pretty well. I might actually pour some samples quick here while this is running. We're on 41. I'm gonna grab another rack. One thing that's important is to make sure you know where you're at, because basically, I know I have 44 and it goes in 44. It may sound simple, but if you get off by 1, it's a big problem. So we've analyzed all of our standards. We have all 6 of these points plotted now. The instrument has done that. I'll make this big so you can see it. And it's in a nice linear curve, almost 1, 9,99996 for the correlation coefficient. Our minimum is not 2 9s and a 5, but that passes that very well. And looking at everything else, this curve looks like it should work well, and we'll continue running the instrument. So right now, this IPC stands for Instrument Performance Check, and a check blank is what it's running next. And it'll run these 2 standards every 10 samples, and that's just to show that the instrument does not drift out of calibration by checking a midpoint standard and a 0. These first 3 green ones here are a lab fortified blank, which is a test of our spike solution. We spike 1 sample every 10 to show that we can recover the phosphorus and there isn't a matrix interference. And then a laboratory reagent blank, which shows that we didn't contaminate or have any issues with contamination when we set this up. And then this QCS is another source of phosphorus different from these standards, and we check that just as a second check against the standards we've made. We purchase a standard from another company or vendor, and it's just a double check on what we're doing. So in most of our quality control, it's plus or minus 10%. This standard is supposed to be 0.50. It's 4944, so it's well within 10% of its value. The instrument is also set up to automatically, that's right, where it grade these, so it says that it's within 10% of its true value, so it keeps running. If it were not, the instruments are nice that they're automated. It will stop and throw up a window and says, this failed. What do you want to do? Do you want to keep running? Do you want to do something? So these instruments are nice in that sense. So that's going to just keep running. We'll check in on those in a second and see if those pass their quality control parameters, and then we'll start getting into unknown samples. Usually these runs are about 200 test tubes or cups. Cup refers to the slot long, so usually out of those 200 cups we get about 150 samples ran. The rest of it's all quality control. So a large portion of our runs are to make sure our numbers are okay. This is my lab fortified blank, so this is basically lab water that we spiked with a known amount of phosphorus. The true value is supposed to be 0.3. It's 0.3056, which is well within 10%, which is the quality control limit. And what we do is every 10 samples, we put that 0.3 milligrams per liter of phosphorus, and just to check that we can recover a known amount of phosphorus in each group of 10 samples, which shows us that there's not a matrix interference from those samples themselves. On the X here we have time in seconds, and then we have volts. So basically the area is plotted as volts per second, or what does it call it? It calls it volts per second or whatever. So it figures out a peak area based off that, and the peak area being this area is what it's figuring out.
Voltage is related to the
Peak
color of the water?
Right, it's the absorbance, or the voltage would be, easiest way maybe describing it is to the peak height. So peak height is going to be, this isn't really 0 volts and this is 10, but it's something like that. That the voltage would be the measurement to the top, and then your seconds is how wide it is.
But this is a reflection of the absorbance of the water.
Right. Basically, this is more blue. This is actually half as blue because this is one part. This is a half a part of phosphorus in the standard. So that's what this one actually has twice as much, half as much. This is half again because we're down to 0.25. So that's, if we were to look at these in test tubes, it'd be blue, half is blue, half is blue again, basically. Can't hardly see the number, but 3860 is the sample number, and it has 0.012 milligrams per liter phosphorus. And so that'll go along, and as each unknown has its peak area, we'll be able to give it a concentration of phosphorus, because we did run that curve of known concentration and figured out that calibration, and then we'll be able to figure out all of our samples for the day. And if it makes it through these next couple checks, I'll be happy. The green ones, if I look at, this is what we call our tray table. So it's basically the template that the sampler is running by. Each one of these numbers is a position number, and every 10 it's going to go back and do this check standard and check blank. And as long as those check standard and check blanks keep coming back within their quality control limits, the instrument keeps running. I'm happy. It's spitting out numbers, and we get our day's work done. But there, for example, this one is actually 0.6, and this one's starting to scare me, because if that goes over 1 part, I have to do a dilution. Because my highest standard is 1, I can only report out numbers that are within my calibration range, so might have to do a dilution on that one.
That would mean that
it's going to be,
this has more phosphorus in it than you expected?
It's going to be just under 1, it looks like. So I won't have to do a dilution.
So
here, that's my 1 standard. If I look at the height of this, it was very close. I said it's going to be real close, but it looks just a little shorter. So, and it turned out to be 0.99, so I can take that number because it's within my calibration range. My calibration range is from 0 to 1.0. If this would have been 1.2, I would have had to do a dilution and then run it again so it was within my calibration range. We have the instrument running, and it seems to be running well. We'll let it continue out. It's 186 cup, or test tubes, whatever you want to call it. A cup is what we refer to the position number, but you can think of it as the test tubes in the rack. Something interesting, this one is actually over 1, so I'll have to do a dilution and run that at the end so it's within my calibration range, which is, once again, is from 0 milligrams per liter to 1 milligram. And since that's greater than 1, I'll have to reset that with a dilution. But what I will do now is continue to load the instrument up with more samples, but also in my LIMS, Lab Information System, I will make a file, which we call a QA worksheet, and I will put in all my blanks, duplicates, spikes, second source samples, and it will grade them and tell me if they passed or not. Most of the limits for this instrument are just plus or minus 10% for those values. So to kind of finish up here, I have my instrument loaded up with its 186 samples it's going to run. This will continue to run till about 3:30, 4 o'clock. What is it? It's 11:15 now, so it'll run for quite a while. During this time, I'll check up on it occasionally to make sure everything's still passing, and also enter the QC data as it is spit out. The numbers for the dupes and the spikes. Make sure if I need to make any notes about any problems. But essentially it'll finish up and hopefully no problems or issues, and shut the instrument down, rinse the instrument out with water, and turn it off and do what I need to do to clean up. Then I will start to work on that data packet that I had showed you, that I will compile the run report, the quality control report, and then make an electronic file to send the results into our lab information system. Another analyst will review that, and if no errors or corrections are found, they will sign off on that. I will electronically send those results into our LIMS system. So for sample 1, 2, 3 has a result of whatever for phosphorus, and then our data entry people will take care of creating the report, whether it's an email, a fax, or an actual paper report that gets sent in the mail, and that'll be on its way.
I'm Julie Mabey, and I manage the data for the inorganic lab. And so when the reports are ready to go out, this would be one of the reports, and with the total phosphorus on it, and it shows the analysis date, the result, the method, and the units LOD and LOQ. And it also includes phosphorus on this particular sample. This was submitted by the self-help samplers for DNR. Okay, then I have another report here. This is done for the UW Arboretum, and they asked for total phosphorus and total dissolved phosphorus, both, so they're both on there. And that was a surface water sample, and they do sampling, every few months, I guess, in the summer.
So what other kinds of samples do you get?
Well, we get a lot of drinking water samples, lake samples, just private citizens, a lot of different things.
Yep.